Let's discuss Newton's second law in rotational motion. As we know, when we talk about translational motion, we can say in translational motion, summation of all forces acting on body can be written as mass into acceleration. Net force on a body can be written as product of mass and acceleration. Similarly, when we talk about rotational motion, the force will be replaced by its angular counterpart, that is torque, and acceleration will again be replaced by its angular counterpart, that is angular acceleration. So we can write similarly in rotational motion, we can write sum of all torques acting on a rigid body is equal to I alpha, because the angular counterpart or rotational counterpart for mass can be written as moment of inertia, and for acceleration we can use angular acceleration. We know well that for a given body of mass m, if a force F1 is applied onto it from left to right and another force F2 is applied onto it from right to left, and say here if F1 is more than F2, we can say the body will be displaced toward right with acceleration A, and the equation of motion for the body we can write as F1 minus F2, that is net force acting on the body in the direction of motion, which is equals to ma. This is the equation of motion according to Newton's second law in translational motion. Similarly, say we are having a rigid body which is pivoted about a given axis of rotation, and say the body is experiencing a force F1 onto it at a particular point, and another force F2 is applied onto it at another point. So these points are A and B. Here we can see due to the force F1, the body will experience a torque in anti-clockwise manner, and due to the force F2, the body will experience a torque in clockwise manner. If we wish to find out the torques, we can drop the perpendiculars from axis of rotation to the line of vector of forces, the direction along which the forces are acting. So if this distance is R1 and this distance is R2, we can see the torque due to the force F1 is F1 R1, and that due to F2 is F2 R2. And say in this situation, if the torque due to the force F2 is more than that of F1, the body will rotate with an angular acceleration alpha in clockwise manner. And here, equation of motion for the rigid body can be written as F2 R2 minus F1 R1 is equals to I alpha. Similar to this, where we are writing the net force acting on the body is equal to product of mass and acceleration. In this situation, the net torque acting on body, as the two torques are in opposite direction, we have subtracted the two. It is F2 R2 minus F1 R1 is the net torque acting on body along the direction of rotation, which can be written as product of moment of inertia and angular acceleration. This is the way how we use Newton's second law in case of rotational motion. In this situation, the body is rotating clockwise with an angular acceleration alpha. In this example, we are given with a uniform rod of length L and mass m, which is hinged at the topmost point, and this released from a position where it makes an angle theta with the vertical as shown, and we are required to find the acceleration of the tip of this rod just after it is released. Now in this situation, we can see when we release it, due to the effect of weight on the rod, this will start rotating in clockwise manner. So if we find out the torque on rod due to its weight, torque on rod just after release, we can write the torque can be given as mg multiplied by the distance of mg from the axis of rotation. Here is the axis of rotation. This can be written as L by 2 sine theta. So this is the torque acting on it. And if we talk about angular acceleration of body, angular acceleration can be given as torque upon moment of inertia. So it is mg L by 2 sine theta divided by the moment of inertia of rod about the axis of rotation passing through its end, it can be written as ml square by 3. So here m and l gets cancelled out. The result will be getting as 3g by 2l sine theta. And in the problem, we are required to find the acceleration of this step, as the rod is starting with angular acceleration alpha. Then the tangential acceleration of the rod can be given as this is L alpha. So this can be written as 3d by 2 sine theta. This will be the answer of this problem. Let's analyze now the motion of Atwood's machine with the friction between a string and pulley. As we have studied about Atwood's machine in laws of motion also, but there we have taken ideal cases of a string and pulley where both pulley and a string were frictionless and a string actually slips over the pulley surface. Here we assume a friction is present and a string does not slip over pulley surface. So in this situation, say if the mass m2 is more than m1, this m2 will move down and m1 will move up. And in this situation, as the friction is present, the string does not slip over pulley surface and the pulley will also rotate. So this m2 is coming down with an acceleration a, and by constraint relation in this mass m1 will also move with acceleration a, as the string is ideal, and the pulley will rotate, and angular acceleration of pulley we can write as a by r, because the particles on the surface of pulley will move with the same acceleration a, and if pulley is rotating at angular acceleration alpha, we know that the tangential acceleration of any body rotating at angular acceleration alpha we can write as r alpha. So using that expression I can write that angular acceleration is equals to a by r. Now the tensions in the two strings will be different. Here it is T2 and here it is T1. Because of friction between a string and pulley, tension can never be same unless the system will be at rest. Now in this situation, if we write the equation of motion of all the particles, for m2 we can write it as m2g minus t is equals to m2a. So this is our first equation of motion. As m1 is going up, we can write this for this m1, this tension is T2. For this m1, we can write T1 minus m1 g is equals to m1a. That is our second equation of motion. So these are the similar motions which we already studied in the topic of laws of motion. Now for pulley, if we write the motion equation, the pulley is rotating in clockwise manner. So there are two torques acting on it if we carefully see. One is due to the tension T2 which is in clockwise manner, and other is due to this tension T1 which is anti-clockwise. So net torque on pulley we can write as T2R minus T1R is equals to its I alpha, and angular acceleration we can write as A by R. This is our third equation of motion. And to analyze the situation, I can take this R on the right side of equality, and if we add the three equations, you just carefully have a look. Here this T2 gets cancelled out, T1 also gets cancelled out. I'll be getting m2 minus m1 into g is equals to m1 plus m2 plus I by r square into a. So on solving, I'll get the acceleration of the blocks, that is m2 minus m1 upon m1 plus m2 plus I by r square into g. This is a way how we find the acceleration of the blocks in case of an Atwood's machine. If a string does not slip over the pulley surface, it will rotate the pulley along with it, and pulley is also having a moment of inertia I. Using this acceleration from equation 1 and 2, we can also find out the tension in the two strings very easily. So be careful about such type of cases when we apply Newton's second law for translatory motion as well as rotational motion simultaneously, and we handle the problem.